Okay, here we go with the Chapter 8 Homework B review. So this week was another homework assignment about primarily gas laws, but taking things a little bit further than we did last time. The average this week was 9.63 out of 12, which is a little bit lower, but within the noise from last year, so we did pretty well on this one overall. So the topics that we're going to cover, there's sort of two major areas of focus on this assignment. So one is what we refer to as Dalton's law of partial pressures, which deals with mixtures of gases and how their pressure and volume and all those things behave. And then the second major topic that we'll cover in this review is going to be what's called the kinetic molecular theory of gases. This is sort of a molecular or atomic level view of how gases behave and sort of relates things at the microscopic level to those parameters that we learned about for gases, namely pressure and volume and all those things. So we're going to go through both of those, primarily numerical questions to start related to Dalton's law, and then closing off with a bunch of conceptual questions related to the kinetic molecular theory. All right, so the first things we're going to get into deal with Dalton's law of partial pressures, and it really still is rooted in the ideal gas equation, which was what we used all the time last week on the homework assignment. The only difference in this case is that we're dealing with more than one gas mixed together. But keep in mind that the ideal gas equation applies to any gas, and it doesn't matter what gas you have. And so what this really means is that when you have a mixture of gases, each gas sort of behaves individually, and then the sort of the total pressure would be the sum of all the gases that are present. And that's what we have to keep in mind here. So we have, in this case, a mixture of SO2 and CO2 placed in a 750 milliliter container at 50 degrees Celsius. We want to know what the total pressure in this container is. So we're still going to use PV equals nRT, but the difference here is that when we deal with mixtures of gases for N, we can either calculate pressure for each individual gas, or in this case, since we're looking for total pressure, all we need is the total number of moles of gas. So we can sort of rewrite this same equation, but just put a little subscript, TOT for total, meaning that if we just want to calculate the total pressure, we just need the total number of moles of gas. It doesn't matter what gases they are. So we have the masses of the two gases, so we can basically just find the moles of each and then add them together. So if we want to find the moles of SO2, I'll use the abbreviation N in the context of gases as we normally do. We have 5 grams of SO2, and the molar mass of SO2 is about 64.1. And so what we get for this is 0.0780 moles of SO2. We're going to do the same thing for CO2. We have 5 grams of that as well, but we have to use a different molar mass because it's a different gas. And the molar mass of CO2 is 44. So this is just mass to mole conversions, which we've been doing relentlessly for the last few parts of the course. And so what we get for CO2 is 0.114. And then the total number of moles is just going to be those two numbers added together. So that's how many moles of SO2 we have, and this is how many moles of CO2 we have that we just found. So when we add those together, we get 0.192, carrying one extra significant figure for now, just so we don't have too many rounding errors. So that's our total number of moles of gases. And again, as we talked about at the beginning of this problem, for the ideal gas equation, it doesn't matter which gas this is, or even if it's a mixture of gases. If we know the total number of moles, we can find the total pressure. So that's what we're solving for here, total pressure, which is just going to be the total number of moles times RT over V. And so we're going to put that number in for moles. Our universal gas constant R. And then the temperature in this case is 50 Celsius. We have to convert that into Kelvin. So that's going to be 323. And then the volume of the container is 750 milliliters. That has to be in liters for the units to work out. So we're going to call that 0.750 liters. So when we multiply all this out, give me 1 second. That seems high. We get 6.79 atmospheres. Let me double check that number, but I think it's right. Just a little bit higher than I expected. All right, that looks right. So that's going to be the number. I think this is a multiple choice question, so you would have just picked the answer that was closest to whatever that is. That's probably one too many significant figures, but that's fine. So that's how you would do this problem, where you're going to just use the total number of moles of gas to figure out the total pressure. All right, the next problem I have is related to this, but this time we're dealing with a little bit different situations. We have 3 gases this time instead of 2, and here we're giving you the percent by volume. So what percent by volume means is if you had 100 liters of these gases and you could then separate them out into their individual components, separate the mixture, you'd get 50 liters of O2, 25 liters of nitrogen, 25 liters of chlorine. So it's a volume percent in this case. And we have the total pressure given as 1.4 atmospheres. We want to know which of the following statements is true. And so basically the statements deal with the mole fraction of each gas and the partial pressure. So the relevant sort of relationships that we need here is, first of all, if you have, there's not really an abbreviation for this, but if you have a volume fraction of an ideal gas, that's going to be the same as the mole fraction. Now the reason for that is because in PV equals nRT, volume and number of moles are proportional to each other, and so the relative amounts in terms of volume and moles are going to be the same if you're talking about a fraction. So remember that the volume fraction is going to be the volume percent divided by 100, and then the mole fraction is sort of defined as the moles of that gas divided by the total number of moles. So these two numbers are equal to each other. That's going to be fairly important because the first part of this question asks you about mole of all these answer choices is about the mole fraction. Now the other thing that's important too is that if we're talking about a mixture of gases, if we want to find the partial pressure of a gas X, one of the gases in the mixture, that's going to be equal to the mole fraction of X, which is abbreviated as chi, Greek letter chi, so we'll call that chi, times the total pressure. So the partial pressure is always going to be mole fraction times total pressure. So that's what we're going to be basically doing in this problem, is evaluating these situations. So if we have 50% O2, 25% N2, and 25% Cl2, the first part deals with the mole fraction. So in the first one, the mole fraction of Cl2 is 25. That would be the mole percent, which is not really a quantity we usually use, but its mole fraction would be 0.25. So if we're talking about mole fraction for each of these, for O2 it would be 0.50, it's just the percentage divided by 100, mole fraction, volume fraction being the same, 0.25 for N2, 0.25 for Cl2, they all add up to 1, and again, mole fraction, volume fraction being the same number. So this first one can't be right because the mole fraction is incorrect. For B, the mole fraction of N2 is 0.25, that is correct, and its partial pressure is 0.25 atmospheres. So if we want to find the partial pressure of N2, it's going to be the mole fraction, which is 0.25, times the total pressure, which is 1.4 atmospheres, and that's not going to be equal to 0.25. That's going to be, I think, 0.35. Make sure I did that right, because I'm bad at doing math in my head. Yeah, 0.35 atmospheres. So the partial pressure of nitrogen would be 0.35 atmospheres, not 0.25. So that number is wrong, which means that answer choice is also wrong. And then if we go to choice C here, so this is choice B. Choice C deals with the mole fraction of O2 is 0.25. That's already wrong because the mole fraction of O2 is 0.5. So that number is wrong. We don't have to worry about evaluating the rest of it. And then finally for choice D, the mole fraction of O2 is 0.50. That's true. And then the partial pressure is 0.7 atmospheres. So the partial pressure of O2, if we calculate it out, would be that correct mole fraction of 0.5. Total pressure is still 1.40 atmospheres for the whole mixture. and that comes out to 0.70 atm atmosphere. So that one is the correct answer. The mole fraction given correctly and the partial pressure given correctly. So whenever we're dealing with mixtures of gases, if we want to calculate the partial pressure, this is going to be the key equation for doing that. And we have to realize then that mole fraction, if we don't know the moles of each gas, can also be given by the volumes of each gas, but expressed as a ratio, not as a percentage. All right. And then finally, this last related question here is going to use the same concept, but in this case, we're not given exact numbers. We're just told the total pressure is 300 torr. We have equal masses of neon and argon. We want to know what is the partial pressure of neon and torr. And the hint here is to find the mole fraction of neon. So we are going to look for that because we want the partial pressure of neon. As we just said, partial pressure of any gas in a mixture is going to be the mole fraction times the total pressure. Okay, so this number we have, but we don't know anything about the amounts of the gases we have except that the masses are equal. So we're not telling you how much of each gas we have. Now, we could do this sort of algebraically or in sort of unknown terms. So what we could say is that, X, we have equal masses of each. So basically we could say that X is the mass of each gas, which we don't know what it is, but it's the same number for each. And then we would say that the moles of neon are going to be X divided by the atomic mass of neon, and then the moles of argon are going to be X divided by the atomic mass of argon. So we could do this algebraically because then once we have the moles of each gas, we can find the mole fraction, but it's a little bit more ripe for error because you're going to have to be dealing with fractions that have unknown variables in them, X, and the chances of messing that up I think are a little bit high in my opinion for a lot of people, for myself included. So the way that I would approach this problem is let's just assume some mass of each gas. It says they're equal. It won't matter what that mass is. The partial pressure will be the same no matter whether this is 1 gram of each gas or 1,000,000 grams of each gas. As long as the masses are equal, you'll get the same mole fraction and the same partial pressure. So let's just assume a certain mass of each gas, and we'll kind of sort of do things a little bit approximately here. I think this was also a multiple choice question, but essentially, if we look at the atomic mass of each gas, the atomic mass of neon is around 20 grams per mole, and the atomic mass of argon, which is the other gas in the mixture, these aren't exact numbers, but they're going to be close enough for this type of problem, especially if it's multiple choice, is about 40 grams per mole. So to make the numbers easy for ourselves, we can assume any mass that we want. Let's just assume though, because the atomic mass is 20 and 40, let's assume that we have 40 grams of each gas. That'll allow us to easily calculate mole fraction, okay? So I like to do it this way just to work with real numbers and not with unknowns, having X's and Y's and all those kinds of things in the equations. So let's just assume we have 40 grams of each gas, a nice round number that we can divide by the atomic masses. And then what that means is that the moles of neon, if we have 40 grams, it's going to be 1 mole of neon has a mass of 20 grams. That's the atomic mass. And so we get 2 moles of neon. Again, we're not doing super exact calculations here. We don't need to for this problem. And then the moles of argon, we would have also 40 grams of that. Its atomic mass is right around 40. And so we get 1 mole of argon. So working with just nice, round, easy numbers, but like I said, you can assume any number you want. It doesn't have to be 40, and you'll still get the same answer eventually. So then what we need is we need the mole fraction of neon. So we have 2 moles of neon, and its mole fraction is going to be divided by the total number of moles. So it's going to be 2 moles. Let's just leave that off. 2 moles plus 1 mole, which is the number of moles of argon. So this is going to be 2 over 3 or 0.66667, so on. And then finally the total pressure, the partial pressure of neon, which what we want, is going to be that number 2 over 3 multiplied by the total pressure. That's the one number we actually have here, which we need, which is 300 torr. and so we would get basically 200 torr. Now it would probably be a little bit different than this if we use the exact atomic masses, because the atomic mass of neon is 20.18 and the atomic mass of argon is 39.95, but to a good approximation, this is what we get, and I believe the answer choice is this is as precise as it was, so 200 torr would be the one that's correct in this problem. Alright, so this problem was a little bit more challenging because we didn't give you all the numbers, but you had to basically just assume some number or use, you know, unknown variables x. It would have come out the same either way, however you chose to do this. Alright, and then the last couple of problems we want to deal with, which it doesn't immediately strike us as being related to the same concept, but it is that we have these problems which we deal with collecting a gas over water. And so essentially what you're doing is you have a closed container of water, or sort of like an inverted burette sometimes, but whatever the situation is, you have, you know, water that you're collecting a gas over. So this is water, and then you're collecting the gas up here. And the important point of this, whatever the apparatus is that you're using, is that the total pressure that you have above the water vapor, above the water, is going to be the pressure of the gas that you're collecting plus the water vapor pressure. Okay, so as we started learning in Chapter 9, we're not going to do a detailed discussion of vapor pressure. It's actually one of the topics we omitted because of the truncated semester we're in with the extra week off earlier. But vapor pressure is basically whenever you have a liquid, there's going to be some amount of gas molecules of that liquid that are above the surface, and that's what gives us, you know, humidity and all that stuff. And so when you have water, when you have a container of water, there's going to be some molecules of water in the gas phase above that are going to contribute to the total pressure. So this is still a statement of Dalton's law of partial pressures. You have a mixture of two gases, the gas that you're collecting and then the water vapor that naturally exists, and the sum of those is going to equal the total pressure. And so that's what we're going to be doing here, because in these types of problems, if you forget this relationship, you're going to get an answer that's close to the right answer, but it's not going to quite be correct if you don't account for the water vapor pressure. So here we're collecting 957 milliliters of hydrogen, 25 degrees Celsius, and the pressure is 765 torr. So the pressure that we give you here, that's going to be the total pressure of the gas mixture that we collect. The pressure of water vapor is 24.0 torr. What is the mass of hydrogen? So again, we're going to start with this relationship here. The total pressure, which is 765 torr, is equal to the pressure of the gas that we're collecting plus the water vapor pressure, which is 24 torr. So that means the pressure of the gas, which in this case we'll just be more specific, this is hydrogen that we're collecting. The pressure for H2 that we're collecting, and it's important to remember that this is H2, not just H, is going to be 765 minus 24, or 741 torr. Okay? So when we want to figure out how much of just the gas we have, in this case we're looking for the mass at the end of the day, we want just the pressure of that gas. And the pressure that we're given in the problem, which is the sort of, I guess, pressure that's surrounding the vessel that you're collecting it in, that total pressure is again going to be equal to the sum of the gas pressure and the water vapor pressure. So now that we have this, if we want to find the mass of hydrogen, all we have to do now is find the moles of hydrogen first, and then convert that to mass once we have it. All right, and so this now just becomes a regular old ideal gas problem. So when you're collecting a gas over water, this is sort of the more conventional or more typical problem type. You just have to do this step first to make sure that you subtract out the water vapor pressure to get the pressure of the gas, and then from there it just becomes an ideal gas problem. So to find the moles of hydrogen, we're going to rearrange PV equals nRT, and so the moles of hydrogen is going to be the pressure of hydrogen times the volume divided by RT. So this is just the ideal gas equation. 741 torr, we have to convert that to atmospheres to be able to use the ideal gas equation. So 741 divided by 760 is 0.975. So that's our pressure of hydrogen in the correct units of atmospheres. Just divided by 760. The volume is 957 milliliters. We have to convert that into liters again to use the ideal gas equation as we saw earlier. And then RT at the bottom, so universal gas constant. And then the temperature is 25 Celsius or 298 Kelvin. So when we work this out, what we get for the number of moles is 0.0381. And then if we want to find the mass of hydrogen in grams, we're just going to take that number, 0.0381 moles of H2. And it's important again to remember what the standard state of all these gases are. Most nonmetal gases are, except for the ideal gases, are diatomic. So hydrogen would be H2. And so when we want to find the molar mass of that to convert to grams, we're going to use 2.02 grams per mole because it's 2 hydrogen atoms in one molecule. So the correct molar mass is 2.02. So when we multiply that out, we get 0.0770 grams of H2, and that would be the number that you would enter in. All right, so that's how we would handle that problem, a pretty typical one. And then the last one I want to do in this section is a lot more involved, although it is a lot of the same concepts. So we have a sample of damp air in a 1 liter container exerts a total pressure of 741 torr. When it is cooled to minus 10 degrees Celsius, the water vapor freezes to ice with negligible pressure, and the pressure is now 607.1 torr. How many molecules of water were present in the gas? So this one is more involved. It's because we're dealing with 2 different temperatures here. So what we're going to basically do is let's think about the situations that we have. So when we're at 20 degrees Celsius, that we're starting with, our total pressure, which is given, 741 torr, is equal to the pressure of the gas is damp air, so I guess we'll call it just the air or the gas pressure. Pressure of the air plus the water vapor pressure. So same concept as the last problem. The total pressure is equal to the air pressure plus the water vapor pressure, but we don't know either of these at this point. We didn't give you the water vapor pressure. That's what we're actually solving for as an intermediate here in finding the total answer. The final answer, and we don't have this either. And then when we go to 10 degrees Celsius, minus 10 degrees Celsius, we freeze all of the water. So the total pressure would still be the air pressure plus the water vapor pressure, but we're telling you that the water freezes as it would at 0 degrees Celsius, and at minus 10 it has negligible pressure. So basically the water vapor pressure goes to 0 at minus 10 degrees Celsius. So at minus 10 degrees Celsius, the air pressure is the total pressure. Basically, that's all we have. The problem is, though, that these two are not equal to each other because, so the 2 air pressures that we have here are not the same because we're at 2 different temperatures. Remember from the ideal gas equation, if we change the temperature, we also change the pressure. So we can't just use 607.1 torr as our air pressure. We have to account for the change in temperature. So the first step we're going to do is we're going to figure out if the pressure at minus 10 degrees Celsius is 607.1 torr, what is the air pressure at the higher temperature of 20 degrees Celsius? So we're going to do first an ideal gas problem. So rearranging the ideal gas equation, P1 over T1 equals P2 over T2. And basically we're going to use P1 is our unknown, T1 is 20 degrees Celsius, T2 is minus 10 degrees Celsius, and P2 is given as 607.1 torr. So that's the first thing we're going to do is we're going to find out what is the air pressure, which I'll call P1, at the higher temperature of 20 degrees Celsius. So it's going to be P2 times T1 over T2, which is going to be 607.1 torr. And then we have to use the temperatures in absolute units of Kelvin. So T1 is the higher temperature of 293. And then T2 is minus 10 degrees Celsius, which comes out to 263 Kelvin. So when we do this intermediate step here, this is not going to give us the answer, but it's getting us in the right direction. We get 676 torr. And so what that means is that at the higher pressure, at the higher temperature of 20 degrees Celsius, the pressure of the air is 676 torr. And so now we can figure out what the water vapor pressure is. So the pressure of the water vapor pressure at 20 degrees Celsius is going to be the total pressure, 741.0 torr, and I probably should give one more significant figure here, so let's call that 686.4. Not that it's going to matter too much, but anyway, the pressure of the water is going to be just the total pressure minus the pressure of the air, 676.4. And so what we're left with is a water vapor pressure of 64.6 torr. And then converting to atmospheres by dividing by 760, that's going to be 0.850 atmospheres. All right, so that was sort of an involved process just to get the partial pressure of water. Now that we have it, we can find the number of moles of water by just doing PV over RT for water. So we just found that the pressure of the water vapor is 0.085. The volume of the whole thing is 1 liter. And remember, both gases will occupy the full volume, so we don't use different volumes for each one. It's just the total volume. And then 0.0821 liter atmospheres per k-mole, and the temperature that we determined this at was the higher temperature, 293 Kelvin. All right, so what we're going to get for that is we get 0.00353, make sure I didn't miss any digits there, 353 moles of water. All right, that's how many moles of water we have, and so then the number of water molecules is just that number times Avogadro's number. So now we're just using the definition of a mole. We have 6.022 times 10 to the 23rd molecules in 1 mole. And so what we should get is something like 2.13 times 10 to the 21st molecules. All right, this was quite possibly the most difficult problem in the whole assignment. So if you had it, there's a lot going on here. There's a lot of chapter 8 topics. So if you got the answer, that's great. If you hopefully can follow it now, it is a very good problem for really doing a lot of different concepts all in one. All right, so to kind of recap what we did, we had to first use an ideal gas equation here to figure out what the air pressure was at 20 degrees Celsius. And then once we had that, we could figure out the water vapor pressure by difference. That's what we did here. And then once we have the water vapor pressure, it's just going to be using the ideal gas equation once again, and then Avogadro's number to finally get the total number of molecules that we have. So a lot of steps there, and there probably are other ways to approach this problem. So if you got the right answer some other way, I'm sure what you did is valid, because there's not really a way to luck into this answer. So if you had other ways you thought about doing it, we can discuss those if you're not sure if what you did was correct, but this is the way that I sort of approach this problem, and that I think is the most straightforward. All right, what we're going to finish up here is mostly conceptual questions dealing with kinetic molecular theory, which is sort of, again, the theory that links the macroscopic properties of gases, their pressure, temperature, volume, all that stuff, to sort of microscopic behavior, how fast they're moving, other things about their movement and behavior at the atomic and molecular level. So the first question here, we have 2 1-liter samples of gas, 1 hydrogen and 1 oxygen, both at 1 atmospheres and 25 degrees Celsius. Which statement accurately describes the gases? And the statements are dealing with kinetic energy and molecular speed. So I think we sometimes tend to overcomplicate these problems a little bit. What we have to understand about gases is that the average kinetic energy, which is abbreviated as Ke with a bar above it, is proportional to the temperature. And that's all that determines the average kinetic energy. It doesn't matter what gas you're talking about. If the temperature is the same, the kinetic energy is the same. And so if we have H2 and O2, if they're both at the same temperature, that means they both have the same average kinetic energy, okay? So because they're at the same temperature, the average kinetic energy for H2 and O2 has to be the same in this problem. And then if we want to deal with the molecular speed or velocity, remember that the definition of kinetic energy is 1/2 mv squared. This is the sort of physics definition. We're not going to actually use this equation, but what it leads us to, I'm not going to do the full derivation, but I did do it during class if you want to look back at that section of the video in the notes. Basically what it leads to is that the root mean squared velocity, as it's called more precisely, but this is just what we would call molecular speed, kind of an average molecular speed. There's always a distribution. This is going to be proportional to 1 over the square root of the molar mass. Okay? So what this basically tells us is that at a given temperature, gases will have the same average kinetic energy, but how fast the gas molecules are moving on average depends on the molar mass, and it's an inverse square root dependence. So the heavier the gas, the higher the molar mass, the slower the average speed, the lighter the gas, the faster the average speed. And so what that means is if we're comparing the average speed of the two gases at the same temperature, remember that O2 has a molar mass of 32, and then hydrogen is the other gas, which has a molar mass of about 2 grams per mole. And so that means at the same temperature, this one is going to be, on average, moving slower, and this one's going to be faster. The lighter gas moves faster on average, the heavier gas moves slower on average. So now we're ready to go through and evaluate these answer choices. So the first three deal with average kinetic energy, which we said should be the same for both because they're at the same temperature. So average kinetic energy of O2 is greater, that can't be right. Average kinetic energy of O2 less than, that can't be right. But choice C, the average kinetic energy of the molecules of O2 is equal to H2. That one is correct because they're at the same temperature. And then choice D was about molecular speeds. It says the average molecular speeds of O2 is greater than H2. That's the opposite of what's actually true because O2 is heavier, it's going to have a slower average molecular speeds. That one's wrong also. So choice C is the only answer here that checks out. So if you're asked about average kinetic energy, all that matters is temperature. It doesn't matter what the gases are, just the temperature is what determines that. But then here we're going to take this same concept and really, again, just look at it in a slightly different way. So we want to know which gas has the molecules with the greatest average molecular speed. And as we said, the average molecular speed, or VRMS as it's sometimes abbreviated, is proportional to 1 over the square root of the molar mass. I think there's an exact equation for this that we're not going to use. I think it's like 3/2 times R divided by those. It's a square root. I think it's the exact equation. I hope I'm remembering this correctly because I don't have the notes in front of me. Is 3RT over the molar mass or something like that. All right, double check. This is the correct equation, but we're not actually going to use this equation, which is really the reason I didn't know it off the top of my head very well. But this is the important part, again, is that the average molecular speed is inversely proportional to the square root of the molar mass, meaning that the heavier the gas, the slower. So we're looking for the greatest average molecular speed. We're looking for actually the one that has the lightest or the smallest molar mass. And so if we just do approximate molar masses for these, nitrogen is 28 grams per mole, CH4 is 16 grams per mole, so we'd have to calculate these at least roughly. Krypton, I don't even remember what that is. It's an element, but I think it's like 80 something. So the atomic mass of krypton is like 83.8 grams per mole. Helium is 4 grams per mole. And CO2 is 44 grams per mole. All right. So if we want the one that has the greatest average molecular speed, we want the one that has the smallest molar mass, which is going to be D, helium. Okay. So those are really the two key concepts for kinetic molecular theory. Dealing with average kinetic energy, which only depends on temperature, and then if you're talking about molecular speed at a given temperature, then it depends on molar mass. All right. And then the last two problems are going to deal with, the next two problems, there's one more after that, sorry, getting ahead of myself. But the next two problems deal with the one application of that equation. So again, we're not going to use this exact equation here so much as we're going to use sort of the relative speeds or relative rates of diffusion, effusion, and so on for two different gases. So effusion is how fast a gas leaks, diffusion is how fast a gas travels down a straight path, and that's going to depend on how fast they're moving on average. And so we can use sort of this concept here about the velocity being proportional to the inverse square root of the molar mass to derive equations that relate relative rates of effusion and diffusion. All right, so we have an unknown gas Q effuses 1.56 times as fast under the same conditions as xenon gas. What is the molar mass of Q? And so the equation we're going to use are sort of two forms of it. If we're dealing with the rate of effusion or diffusion, the rate of the unknown over the rate of whatever the other gas is xenon. So the ratio of these two rates of effusion is going to be related inversely to the square root of the molar masses. So it's going to be the molar mass of xenon over the molar mass of our unknown Q. Okay, so if we're dealing with rates, which is how fast the gases are, which is related to how fast the gases are moving, again, they're inversely related to molar mass. So this is the form of the equation we're going to use. If the rate of Q is in the numerator, the molar mass of Q is in the denominator of the square root, and likewise vice versa for xenon. So now we can start putting in numbers. So basically the ratio of the rates, we're told if Q effuses 1.56 times as fast, that means the ratio of the rates is 1.56, larger for Q than xenon. And that's going to be equal to the square root of the molar mass of xenon, which the molar mass for xenon is, I think, is 121. Let me make sure I get that number right. Sorry, 131. So the molar mass of xenon we can get from the periodic table is 131.29 grams per mole. And then that's going to be over the square root of the molar mass of Q, which is our unknown. All right. So then all we're going to do, this algebra is a little bit different than we're used to, so I'll go through it quickly. We're going to square both sides to get rid of the square roots. And so what we get then is 1.56 squared is, so 2.4336, I'll just keep some extra digits, is equal to, we get rid of the square roots, it's going to be 131.29 divided by the molar mass of Q. And then if we just do some algebra, cross multiply and divide, the molar mass of our unknown Q is going to be 131.29 divided by that 2.4336. So it's going to come out to 53.9 grams per mole, or somewhere in that ballpark. This was a problem that had variable input. So basically this number here, 1.56, could have been any number of possibilities, but this is how we would approach it. So if we're dealing with the rates of effusion or diffusion, it's going to be inversely related to the molar mass. If we go to the next problem, this one is set up very similarly. It's also an unknown gas Q. We're solving for its molar mass once again. But this time we're talking about how long it takes to effuse, how long it takes to leak out of a small opening. So if we're dealing with the amount of time that it takes, recall that if the gas is moving slower, it's going to be a longer time. If the gas is moving faster, it's going to be a shorter time. And so basically, the rate that the gas is effusing or diffusing is going to be inversely related to the time. And so if we want to do a ratio of times, the time that it takes our unknown gas Q to diffuse over the time that it takes, in this case, the known gas is nitrogen, N2, that's going to be equal to a direct square root relationship of the molar masses. So it's going to be the molar mass of Q over the molar mass of N2. And again, the reasoning being that the higher the molar mass, the slower the effusion is going to be. So if it's a heavier molar mass, it takes longer time to effuse. So now we can start putting in numbers for this one again. So the time ratio for the unknown over nitrogen is 2.42, and that's going to be equal to the square root of the molar mass of our unknown, which is Q, we don't know what that is, and then over the molar mass square root of the molar mass of nitrogen, which is 28 grams per mole. All right, and so again, same algebra as before. We just square both sides and then cross multiply. So 2.42 squared is 5.8564, and that's going to be equal to the molar mass of Q over 28 grams per mole. All right, if we square the square roots, we just get rid of the square root signs. And so that means the molar mass of our unknown Q is going to be that number of 5.8564 times the molar mass of N2. So it's going to be 164 grams per mole to 3 significant figures. All right, so very similar problem. We just have to remember that there's two forms of the equation. In the first one we did, in terms of rates of effusion or diffusion, there's an inverse relationship to the square root of the molar mass. If we're talking about the time that it takes something to effuse or diffuse, there's a direct relationship. So make sure we keep those straight and understand that conceptually before we start these problems. All right, and then the last one I want to go through sort of summarizes a lot of things about the kinetic molecular theory and basically how, the speed of a gas and the temperature which affects that speed, how they relate to the pressure. And so basically what the key concept is that the pressure of the gas is going to be proportional to the strength of the collisions of the gas with the walls. So the reason that a gas exerts pressure is because as it's zipping around, as it's constantly moving and colliding with other things, it's going to at various intervals is going to collide with the wall of the container. And when it collides with the wall of the container, that's what exerts the pressure. So how high that pressure is going to be proportional to the strength of those collisions times the frequency, how often that they collide with the wall. Okay? All right? And in a normal situation, if we raise the temperature, the gas is moving faster, and that's going to make the collision stronger. And then if we keep the volume the same, that's also going to increase the frequency of the collision. So normally if we have a fixed volume, if the volume of the container is fixed, if we increase the temperature, so let's write this out more specifically. So if we have a fixed volume, meaning that we're not changing the volume of the container, if we increase the temperature, we're going to increase the average speed of the gas molecules, and that means they're going to have the strength of collisions is going to increase, and also the frequency of collisions. Both of those would increase. And as a result, the pressure increases. So normally if you just have a fixed volume container and you increase the temperature, this is what happens. The speed of the gas molecules gets higher. There's going to be stronger collisions with the wall because they're moving faster on average. They're going to collide with the wall more frequently because they're moving faster on average, and that's going to combine to increase the pressure. But in this problem here, we're telling you that the volume is also increased and the temperature is increased as well. So both of those are going up, and the pressure is constant. So pressure is not changing. So what this means is that we have this situation here. The pressure of the gas is proportional to the strength of the collisions times the frequency of those collisions. But in the situation we're dealing with here, this is staying the same. We're not changing the pressure of the gas at all. Okay? So let's think about what happens. If we increase the temperature, the average molecular speed is going to still increase. Doesn't matter what's happening to the volume. As long as we increase the temperature, the average speed will increase. So that's going to be true. So that should be increases. And then the average force of an individual collision. So if we're talking about the force of an individual collision, that's still going to have to increase, because if the gases are moving faster, if they have more kinetic energy, they're going to have more forceful collisions with the walls. But then the last one here, so that's going to be increases as well. The last one is the one we have to think about. The number of collisions with the wall per second, does it increase or decrease? Well, we're saying here that the pressure of the gas is staying the same. The strength of the collisions is increasing. So in order for the pressure to stay the same, that means the frequency has to be decreasing. All right, so if there are stronger collisions with the wall of the container because the gas molecules are moving faster, they must not be happening as often to be able to keep the pressure the same. So that's sort of, just sort of a little bit of mathematical logic. If this number is staying the same, this number is increasing, that means the number you're multiplying it by has to be decreasing to keep that number constant. So that means in this case, the number of collisions per second, the frequency of the collision, must decrease. And again, that's possible because we're increasing the volume. By increasing the volume, we're spreading out the gas molecules more so they don't hit the wall of the container as often. So the correct answer for this one is going to be increases, increases, decreases, which is going to be choice B. All right. So this was a good problem because it sums up a lot of the key concepts related to how we affect the pressure of a gas when we change the temperature. And again, changing the temperature is always going to increase the speed of the gas molecules. It's always going to increase how strong the individual collisions are. But if we keep the pressure constant, as we did in this problem, that must mean that the frequency of collisions has to decrease. All right, so hopefully that one makes sense to us now. If you have any additional questions on these ones that I went over today or other problems that you had on your assignment, please get in contact with me and let me know. We have a sort of fast and frenzied finish to the semester coming up, so a lot of stuff going on in the next 2 weeks. So please keep in touch if there's anything that I can help you with, and I'll see you guys around.